Okay, super. So we're very glad today to have Professor Aleksandr Rodin to join us to give a condensed matter seminar. So Aleksandr is a theorist, a condensed matter theorist, who's perhaps maybe best known for his work in black phosphorus and graphene plasmonics. And he's worked on a variety of different things, very interesting effects that just go from trying to understand the near-field properties of graphene plasmonics, but also to understand the various strain and gap formation properties in black phosphorus as well, amongst other things. He's recently worked on very exciting things to do with the Casimir effect, and that's what he'll be talking to us about. So the floor is all yours.
All right. Thank you very much, Justin, and thank you, Arpit, for taking care of this and recording. And yeah, thank you for facilitating. So, and thank you everybody in the audience for joining for this, because I'm actually really excited to talk about this. And as Justin just mentioned, we have undergrads, and that makes me actually very happy that there's enthusiasm for this topic. So as the title suggests, I'll talk to you about Phonon Casimir effect today. And the goal of this presentation primarily is to provide you with the machinery to work on this effect. Because as we'll go through this, you'll realize that the big issue that you might encounter is how do you actually solve the problem so you don't mess it up mathematically? Because the trick here is picking the right notation, and then things kind of fall into place, right? As so often is the case. So I'll try to make it more pedagogical, I suppose. And since the seminar is recorded, you guys can go back, obviously, and take a look at it, and obviously screen capture. And right. So I really hope that this presentation will stimulate your interest in the topic. So to start with, I would like to thank Mr. Gideon Lee, who is a recent graduate of Yale-NUS College, for all the work that he's done on this work. It's a collaborative effort here, so he really did a great job here. So he's in the audience, so thank you, Gideon. I would also like to provide you with some references which will be used in this work or in this presentation, or could be of interest. So most of the material presented here comes from reference number 5, which our recent preprint, which is available on arXiv. And obviously, I'm very partial to references 4 and 5. That being said, I do encourage you, if you're interested, to take a look at all of these. The first 3 works are excellent. They take a slightly different approach. They're more diagrammatic. They help you complete the picture. So I believe these 5 references can give you a good starting point if you are interested in the subject. Okay, so as an outline for today's talk, it's going to be kind of broken into these 5 pieces. So we're going to start with an introduction where the goal is to build an intuitive picture, because the math will get quite hairy, or we'll try to make it less awful, but sometimes you have to just bite the bullet and go through. But the important thing is to gain some intuitive feel of what this Phonon Casimir effect is all about. Then I'll give you a presentation on analytic formalism using the path integral approach. Now, if you're not too familiar with path integrals, I understand it might be a little bit challenging, but I'll try to guide you through so that if you're interested and you look up in outside materials, you can kind of piece together the whole picture. Following which, I'll talk about the numerical results and how our field theoretic expressions and results compare with the numerical diagonalization. Finally, from the new things, I'll talk a little bit about displacement statistics and the role that the Phonon Casimir effect plays in the atomic displacement in solids. This is new. This really are the results from this week, so they're a little bit half-baked, but I thought I would share with you. So just to show what's happening now. And at the end, we'll take stock of what happened with little Q&A, if you're interested and, kind of reflect on what just happened. So instead of kind of pontificating on what Phonon Casimir effect is, I think it's better to just start with an example to give you a feel of how it even arises, right? So as a starting point, it's useful to consider a chain of harmonic oscillators, excuse me, that's n masses long, and every mass is the same, right? It has mass m, connected by identical springs with the force constant k, right? So far so good. So what we do next is we freeze two of the masses, right? So we freeze them, hold them in place, prevent them from moving. And what that produces is a segment of length L bounded by these two masses, okay? Now, we know what the oscillatory modes in such a segment are. It's something that you might have solved in your mechanics class and your solid state class. So you know that the energies of the modes in this segment are given by this expression, right? Where you have your characteristic energy root k over m, and then your energies are given by that sine function. And there are L modes, right? If you have L masses in your segment bounded by your immovable red atoms, you have these energies. Now, of course, when we introduce our immovable masses to our periodic chain, we not only create a segment of length L, but we also create another segment on the other side of length n minus L minus 2, right? So the rest of the chain energies are given by this expression, right? And of course, because there are more atoms there, you have more modes. Okay, so far so good. So this we can solve, this is okay. Now, we also know that each harmonic mode, each harmonic oscillator mode, the minimum energy that it can have is essentially 1/2 of its fundamental frequency energy, right? So if we would like to know the total energy of our system in this configuration, the minimum total energy, what we would do is we would sum up the energies in the short segment, divide them by 2, and we can do the same thing, sum of the energies in the long segment, divide them by 2. And fortunately, you can actually perform this summation, and it gives you this, this cotangent term. So if we want to get the total energy of the system, we will just add up these two expressions. Okay, if we do that, we see that as n becomes really, really big, the total energy of the system goes as something of order n, which is a really big number. Okay, fine. And then it's minus some quantity divided by L. Okay, so what that tells you is that the energy, this negative component, gets bigger as your red masses get closer to each other. So in effect, you can think that these red masses are being attracted to each other. Okay, now, this is the essence of the Phonon Casimir effect in its simplest picture. Because if you think back to the traditional photonic Casimir effect, the way it goes is that you have two conducting plates in vacuum, they aren't charged, and they attract each other because of vacuum fluctuations of the electromagnetic field between them. Now, the math there is a little bit more hairy than we have here, but you also get, if you kind of look at it in a 1D way, the interaction goes as 1 over L. So you might ask, well, okay, fine. So in the photon Casimir effect, it's vacuum fluctuations, it's all this exotic stuff. How is this Phonon Casimir effect? Why is it Casimir? Well, remember that this 1/2 energy term it is the vacuum energy of the bosonic oscillatory modes. So really, it's the same thing. It's exactly what we're summing here. It's the kind of the lowest energy state. So your interaction actually comes from this vacuum energy of the bosonic field. Okay, so this is sort of the big similarity, and that's what we call it, the Casimir effect, right? Now, so I hope that gives you a little bit of an intuition of how this works. Now, the interesting thing about phonons, I apologize, is that by cranking up the temperature of the system, we can create more phonons. Obviously, we increase lattice vibration, get more of them. And you might kind of intuitively think, well, you know, more phonons, more interactions, so maybe we can strengthen our Casimir effect, our Casimir attraction, by cranking up the temperature of the system, okay? So let's kind of think about that a little. So we go back to our chain, and let's imagine we take our red mass, this immovable red mass on the right, and we shift it 1 over, okay? So what we've done right now, essentially, we've added an atom to our short segment, okay? Alternatively, you can think about it as moving a mode, a vibrational mode, from the long segment to the short one, okay? Now, we can actually figure out what the energy change that this creates is, right? If we use the expression from the last page, we see that the change in energy at 0 temperature is just given by the difference of the new configuration minus the old configuration, right? So you can see that over here, we have, this is the energy of the new configuration, and this is the energy of the old configuration. So by moving this red mass over, we have increased the energy of the system. Okay, fine. And obviously, the increase goes as 1 over L squared, which you'll notice is basically the derivative, or negative derivative of this term. Okay, so as expected. All right, fine. So this is the 0 temperature. Now, if we increase the temperature of the system, you'll remember that for a single mode, any oscillatory mode, the total energy at a finite temperature is given by this expression.
Yeah, somehow you're muted now. Yeah, I'll ask you to unmute.
Am I back?
Yes, you're back now. Yes, very good.
Oh, that was
Yeah.
weird. That's
yes. Somehow something happened. Yeah.
So if you look at the expression in the square brackets, right, that's just the number of the quanta that you have, right? So familiar with that. So the energy of a single mode is actually given by the number of quanta times the energy of the mode. Now, what's neat is you'll notice that if we crank up our temperature, if we make our T big, you'll realize that the energy of the mode approaches T regardless of what the energy of the mode is itself, right? And we know that from equipartition theorem, right? Like as you crank up the temperature, you just kind of approach temperature. So what's important here, it doesn't matter whether this mode in question lives in the short segment or in the long one, right? Because your total energy of a mode becomes independent of the mode's frequency. So why is that important? It means that if you move the mode from the long segment to the short, as we just did by moving the red mass across, the energy of the system won't change, right? Because the mode doesn't really care whether it lives in the long segment or in the short. So what that tells you is that the change in energy as T gets big goes to 0. Okay, so so the takeaway here is that increasing the temperature leads to a suppression of interaction. And again, it might be a little counterintuitive, right? You'd think more phonons give you more interaction. Not the case. And one way people often look at it is the fact that your finite temperature phonons end up scattering your virtual phonons, right? I am not a huge fan of this explanation because it seems a little bit, contrived. The way I like to think about it is that the Casimir effect rests on the energetics. And once the energy difference goes to 0, obviously you lose the attraction. Okay, so.
Yeah, so I actually have a quick question just to make sure that I'm completely kind of following you here. This is actually exactly analogous to the traditional Casimir interaction. And actually this is an attractive interaction, right? So,
right.
So the two red dots want to kind of go to each other. So, and also you're saying that, T goes to large effect also means that, this interaction is suppressed. So does this also mean that this is a uniquely kind of quantum effect?
Yeah, in a sense, yeah.
Okay.
Yeah, because it rests essentially on the zero energy. It is the strongest when the entire energy comes from your 0-point motion. Yeah.
And this derivation kind of, completely kind of relied upon immovable red dots, right?
At this point, yeah, it's just the easiest to see. We'll relax this assumption later, but for now, it's just the easiest to think about it as them being immovable. The math is just the cleanest.
And are you able to obtain dynamics from this?
Mm-hmm.
Okay, fine.
Sort of.
Yeah, you'll talk about it. Sorry.
It's actually quite, it's sort of. So by the way, that's an excellent point. So the reason why the red dots are immovable, you can think about it in two different ways. And it seems like pedantic at this point, but it will make a difference later. They can be either infinitely heavy, which makes them immovable, or you can confine them in external harmonic potential that's infinitely strong. The net effect will be exactly the same. Obviously, they won't move, right? But as we work through stuff, you'll realize like you have to be a little bit careful when you work out the math in a more kind of detailed way, okay? So if we're okay with this setup, let's actually, do real stuff now. We're gonna write down the general.
Before you move on, can I ask one question? If you go back to the previous slide.
Hold on a second, let me try it.
It's okay. I just want to ask that your difference in energy goes as 1 over L squared. So is that capital L a constant?
Sorry, say it again.
So your difference in energy goes as 1 over L squared.
Mm-hmm.
Is that L constant, the capital L?
No, as you're increasing your L, right? Every time you take an extra step, every time you might move your red dot over 1 to the right, the energy increases as 1 over L, the current L squared.
Yes. So if I keep the L constant and I now increase the temperature, I still expect my difference in energy that it goes to 0.
Correct.
So does it mean that increasing the temperature somehow dumps in more mass into the frozen phonons?
Increasing temperature dumps more mass. How do you mean by dumps more mass? Sorry.
So I mean the difference in energy goes to 0. So so these frozen phonons no longer can interact each other. So does it mean that it's dumping more mass or something into the phonons?
Well, in the sense that the 0-point energy is still there, right? It's just that it becomes overwhelmed by the finite temperature contribution.
I see. Okay. Thank you.
Yeah. So that's really all it is, right? Like, and again, like I'll kind of keep harping on this, that really the best way to think about this is the energy difference before and after, right? Because it's sort of how much free energy you liberate by moving your mass. And I hope like as we go through this, it will become more clear, right? Okay. So no worries. Thank you. So if we consider a general solid with atoms coupled with each other in a harmonic approximation, we can write down the following Hamiltonian. Now here's an important aspect. Usually the Phonon Casimir effect is formulated for crystals, right? Because you have this periodicity of phonons, et cetera, et cetera. It turns out that the math is actually easier if you relax that assumption in the beginning. So treat a more general system because you don't have to deal with extra phonon branches and all that stuff, right? So you can just say, okay, imagine we have a collection of masses labeled by J in the top. Over here, right, you have your pristine Hamiltonian, you have your kinetic energy, you have your harmonic interaction. So P is the momentum of the mass J. It's a d-dimensional vector, right? So D is being dimensionality, works for any dimensionality. U is the displacement of your atom from its equilibrium position. V is the coupling. Okay, so this is our pristine system. And we can also introduce some defects, some perturbation to the system. We will assume that the perturbation is quadratic, both in momentum and in position, right? And generally speaking, we can write down your perturbation here as coupling different atoms, right? The kth and the jth, the kth and the jth here, right? Now, again, importantly, our V, JK, lambda, JK, delta, JK are D by D matrices, right? Where D is the dimensionality of the system, right? Because the big issue here is, the notation. So keep that in mind. Now, you'll notice here that if our lambda is block diagonal, as in if only lambda JJ exists, it's equivalent to changing the mass of one of the atoms, right? We're essentially changing a term that's, proportional to the momentum of an atom squared. If this term is block diagonal in delta, it just amounts to introducing a harmonic well that kind of restricts the movement of an atom. Okay, so that's generally what one studies the most when dealing with the Phonon Casimir effect, right? So right now, lambda and delta are completely general, but later on we'll focus on them being block diagonal, right? So not coupling different atoms, just focusing on a single atom. Now, because we will want to actually work in the path integral formalism, it's useful to write down both displacement and momentum in the following manner, where you have your annihilation and creation operators for oscillatory mode S in the system, right? So this you might be familiar with for a harmonic oscillator from before. But of course, here you have many harmonic oscillators, right? You have many vibrational modes. And epsilon is your polarization vector, right? Because depending on the mode, your particular atom L will oscillate in a particular direction as prescribed by this epsilon, okay? And these quantities are obtained from this, right? So you solve your, you have your dynamical matrix here, you diagonalize your system, you obtain your eigenmodes, and epsilon SL is just a segment of epsilon S corresponding to the Lth atom, okay? So, and then of course, for convenience purpose, we also are going to define this P sub S and U sub S, right? Which is basically your polarization, your eigenvector multiplied by the mass matrix. Now, important, this mass matrix is block diagonal with, mj times the identity on the diagonal, right? Because you need to scale it properly. Okay. So once we plug in all these terms into our Hamiltonian, we get something cleaner, right? We obtain that our Hamiltonian is given by the familiar bosonic phonon Hamiltonian, the H0. We have this number operator plus 1/2 multiplied by the frequency and the defect Hamiltonian on the right, okay? And of course, you'll notice that this P transpose lambda P and U transpose delta U are numbers, right? So U, lambda, and P are all vectors and matrices, but once you multiply them, they just give you a number, right? So it's essentially what it tells you is that once we introduce the defects to the system, your phononic modes or your vibrational modes, S and S prime, start talking to each other, right? They start scattering. That's what that describes. Now, this looks fine, but there's something less than ideal. You will notice that these two terms here are not normal ordered, right? You don't have creation annihilation, right? You have kind of orders are all over the place. So in order for us to do the field theoretic approach to actually do the path integrals, we need to have them normal ordered. So if we commute our B and B daggers to establish a normal ordering, we get the following expression. And you'll notice that at the end, you have this Kronecker delta. So once you commute stuff, you recover a constant term that's independent of the operators. And of course, you get the same thing even for a pristine system, that 1/2 term in your H0 comes exactly from the same thing, right? It's commuting B dagger and B, okay? So the net effect is that this delta gives you the delta in the first expression gives you this P lambda P, and then the second expression gives you U delta U, right? So essentially, you have sort of a constant energy contribution. Part of it is coming this omega over 2 comes from over here. This guy comes from this Kronecker delta and this term, and this guy from the Kronecker delta and this term, right? So we kind of have this. Now, having established normal ordering, we can actually take our Hamiltonian and transcribe it into the action. Turns out that it transcribes fairly well. So basically, each creation operator becomes a phi bar. Each annihilation becomes a phi, right? And you get this expression. Now, it looks a little bit messy maybe, and it's possible to tidy it up a little bit. And this is where notation becomes quite important to make your life easier down the line. We can focus, if you notice here, you have your summation over n, which is the bosonic Matsubara frequency. And it's convenient to first focus on the non-zero Matsubara frequency, which allows you to combine your expression in the following manner, right? So you'll notice that you have terms where phi bar and phi have a minus sign in the middle, and then some which have a plus sign, right? So it's useful then to perform a change of variables as follows, right? Define new fields, new complex numbers, psi, psi plus and psi minus, which kind of correspond to the plus sign or the minus sign between the phi's over here, right? Now you'll also notice over here that psi plus minus, if you change the sign on the Matsubara frequency, the two quantities are related. So in fact, the psi fields are only defined for n bigger than 0. Okay? Because of this relation. Okay? And it makes sense because essentially we introduced a plus and a minus, but the total number of fields has to be the same, right? You can't just create extra numbers. So the important bit from here is that we can transcribe our action from over here to something like this, okay? Where we have a bit which comes from the pristine system. Clearly, this does not contain any deltas and lambdas. And we have a bit over here which comes from our perturbation, okay? Now, what I will ask you to kind of note is I'm referring to this entire thing as minus g. This quantity will show up later. Okay, so it's, if you're familiar with this, it's basically the Green's function, right? But just, remember that this quantity, we're going to use it later. Okay, so if we're happy with that, we can write down the partition function for the system, obviously. So the partition function is just given by the integral of the integral of e to the power of minus action, right? And once we integrate our action from the last page, we obtain the following expression. Now, you'll notice over here that our partition function has a contribution coming from our free energy, from the constant energy, from the 0th Matsubara frequency, and then from the terms from the last page. Right? Now, this term can be, we can use the properties of the determinant. We can pull out this gamma outside and then permute the terms inside the determinant to obtain this expression. Okay, now what is that? This C here explicitly is given by this expression. Okay. Where this thing, this pi, is a matrix of these entries. Okay. So it's more actually useful for intuition if you rewrite this expression like this. What I did, I just multiplied top and bottom by 2 omega. That's all I did. Why is this useful? Well, it kind of tells you what you're looking at. You'll recognize probably this thing over here as the bosonic Green's function. And this thing on the left, it almost looks like a product of displacement vectors. Not quite, it's missing some masses on the bottom, right? So what this tells you, what this pi tells you essentially is how two masses, mass I and mass J, talk to each other via a particular mode omega s, right? That's all it tells you. This tells you how two masses in your systems are coupled to each other, right? Or if you will, it's how a particular mode scatters between one mass and another, right? So that's sort of an intuitive way of thinking about it. Now, I know this is quite hairy, but frankly, I think this is actually the cleanest way to get through this.
Sasha, thanks for this. This sounds like, it's very detailed work. Could I try to maybe understand this from maybe a simplistic point of view? So if I try to take my naive understanding of your Casimir effect, and I said, I wanted to use just kind of a normal kind of field theoretic way of understanding this, could I think of what you're doing basically as you are trying to look at how the defect, which is this immovable mass, is interacting with the other immovable mass via the production of virtual phonons. And so there's some virtual phonon process, and of course, because there's a virtual phonon process, there's a bosonic Green's function. So it's a lot like, for example, the phonon-mediated electron-electron interaction between two electrons. So is this quite similar? And then basically the first, you have this epsilon Si times epsilon Sj divided by omega s. That is some kind of interaction term. The vertex term. Is that what this is?
Absolutely, yeah. You can think about it as a diagrammatic approach, 100%. The difference between here and electrons is that for the electron phonon system, right, you sort of integrate out the phonons and you get the effective interaction between electrons, right? Whereas here, essentially, you only have the phononic fields and the perturbation in the phononic field. But yeah, it's very similar, right? You have, like you said, you have this vertex, which is epsilon epsilon multiplied by the Green's function, 100%.
Yeah, so maybe the difficulty is that, from the standpoint of trying to do it from a diagrammatic point of view, you probably don't really know what the interaction vertex is a priori, right? So if I put in a defect there, it's not super clear to me how to write down the vertex straight away. But maybe what you're saying is your method allows you to very easily identify the vertex.
Yes, but so in fact, so the two of the references that I showed in the beginning actually did it diagrammatically, right? And they identified the vertex. The issue with their approach, there are actually two issues. First, if you do it like in their way, it's really difficult to mix the defect types. In a sense, you either have the lambda type terms where you modify the mass, or the harmonic well term. Mixing them becomes harder, right? Also, what makes it what's difficult is having more than two defects, because here the interaction is not pairwise, right? You can't just calculate pairs of interactions. You have to do the whole thing. So you're correct. You're absolutely correct. It's the same exact approach. It's just harder to keep track of things.
Okay, thanks. Yeah. Thanks a lot.
And then, as a final kind of step here, is you get that, if you perform the same thing for the 0th Matsubar frequency, you get the Z0, which looks almost the same as Z for finite Matsubar frequency, except that you have 1/2 in the power, right? So again, if, kind of gonna gloss over this bit, if you guys, it's recorded, so you can go back and take a look at the expression. So finally, the way we extract our interaction energies from Helmholtz free energy, right? By taking the logarithm of Z, of the partition function, multiplied by -t, we get the free energy. Now, we can write our free energy, we can recast all our terms in the following way, where we have the portion which comes from the pristine system, and we have the defect portion. Okay. And the defect portion can be written like this from our previous expression. You'll again recognize this guy as our constant term coming from the commutation from before. And again, you'll also see here that if our lambda and our delta are block diagonal in impurity, neither this nor this term contain cross terms. They do not contain interaction between defects. So all the interaction should live over here. So this is what you really want. This is the guy that you want. Now, importantly, when we wrote this stuff down, we included all atoms in the system, right? Generally speaking. However, if your atom in a system is not perturbed, you don't need to include it here, right? Because it will give you a zero contribution. So really, your delta and lambda should only include the atoms which are perturbed, which reduces the size of your matrix to a manageable size, okay? Now, to get the interaction energy, we grab this term. Now, this term includes the kind of the interaction between the energies, but also the energies of having the impurity in the system. So what you need to do is you need to subtract from it the equivalent term, but for single impurities, right? Essentially, you get this term for all the impurities in the system, and then from it, you subtract the equivalent of this guy for one impurity at a time to give you the interaction, right? So you get this expression. In fact, it's actually nicer to write it like this, where this Xi diagonal is essentially the same as this Xi, but where you have removed the couplings from different impurities, right? Why is this nice? Because if you're doing it numerically, you create this matrix once and you use it twice, right? You don't have to, suffer by writing extra code. Okay, so the key result is kind of this monstrosity. It looks scary. In fact, it's quite well behaved. Now you'll notice here that I separated the non-zero Matsubara frequency, right? Which is, it's just basically this expression from the 0 one specifically, right? So here's the summation goes for n bigger than 0. Okay, here is the remaining part. Now, you might be wondering, why am I doing this? This bit caused me a lot of headaches. So I'd like you to, avoid suffering if you can. Okay, so why are we splitting this thing away? You first will notice that this bit contains only the delta type perturbation, only the harmonic potential perturbation. There is no lambda here. So let's take a look at this 0 Matsubara frequency. If you look at this interaction energy, you will notice that this first term vanishes at high temperature. All right, because this guy goes as 1 over Matsubara frequency squared. As t goes to infinity, this bit vanishes. This bit on the right, on the hand, grows with temperature. Now, if you recall from thermodynamics, Helmholtz free energy is given by the difference between internal energy and T times the entropy. Okay, so it stands to reason that Fi is a combination of somehow like of EI, internal energy of interaction, and somehow like an entropy of interaction. Now, we know that is from what we showed in the very beginning, the interaction energy vanishes at high temperature, right? That's the first thing we showed. Okay, fine. So we identified this remaining bit with this. Right? Now, why is this important? You will notice in earlier publications, when the calculations are performed, the authors drop the 0th Matsubara frequency without really explaining where it went. Right? Why is it that the energy of interaction does not depend on the 0th Matsubara frequency? And you'll notice that if you talk only about the lambda terms, this guy doesn't matter at all, right? Because it doesn't even show up. But once you have the delta, it plays a role. Now, where can you run into issues? If you want to compare your field theoretic results to exact diagonalization, right? If the system is not too big, you put together your matrix, you diagonalize it, and then you compute the free energy using this expression, right? The familiar free energy for bosonic modes. Now, the free energy of defects can be obtained by calculating, the F with defects minus the F for pristine system. Okay, for the pristine matrix. And then the interaction energy can be obtained by subtracting the defect energy for all defects present minus, the system with individual defects, just as we did for the field theoretical approach. The issue here is that as t goes to infinity, this Fi grows in temperature, grows linearly in temperature. Okay, and what you realize is if you were to drop your 0th Matsubar frequency term here and not be careful about it, and simply try to compare your free energy to this term, you will have a disagreement. Okay, and the reason why you have the disagreement is because of this guy. Okay, so the important thing here is that this term is your TSI. And the takeaway is you need to decide what you want to calculate. If you want to calculate the internal energy, you will drop the 0 Matsubar frequency. And to compare to the exact diagonalization, you have to subtract this term, right? Alternatively, if you want to do the free energy, then don't subtract the term, but do include the Matsubar frequency. Okay, so this is where Gideon and I, smacked our heads against the wall quite a bit because it wasn't agreeing. Okay, and that's where this thing sits. Okay, so as finalized, right? So before I show you the pretty pictures, this is the approach. This is how you calculate this stuff. Okay, so these are the steps. First, construct your matrix M, right? The matrix for the impurities. Construct your delta and lambda matrices. Assemble your delta and lambda. Diagonalize your system. Calculate your pi. Calculate your C. And then perform the summation numerically, right? So again, I'm not going to read this because this is recorded, but these are the steps that we used. And once you've written down the formula, don't overthink it. Just make sure your numerical results work. Now, another bit that for a crystal, right? Because notice we talked about general systems. If your system has a crystalline periodicity, you can use the idea that you have phonons, right? So your pi summation takes this form, where you have here, this is the distance in the between two unit cells hosting the impurities. You have phonon branch index, and you have this index here, which labels the atom in the unit cell. Now, by the way, so one important thing that we did with Gideon in this work is we generalized the solution to an arbitrary number of phonon branches, right? Prior work relied on a single phonon branch, but by starting with the general system where we did not think about phonons, we just thought about individual modes, we got to bypass this complication, right? We just treated them as vibrational modes and said, well, turns out the modes can be categorized as phononic branches. Okay, great. So it's just easier this way, right? Even though it's more general. Okay. All right, fine. So let's take a look at the simplest system that you can address with this. Now, this example is a little bit contrived because you will never do separation on a diatomic molecule. That's silly. You can't separate. The point here is to kind of investigate whether our exact diagonalization results agree with the field theoretic ones, right? So we have this diatomic molecule connected by some spring K and hooked up to the walls with a capital K, right? Just for the sake of generality. And because our formalism was developed completely for a general system, we can actually take a look at Fi, right? Our interaction energy between these two masses. Now again, take it with a grain of salt when it's like interaction energy. I can't actually separate these defects on the diatomic molecule. There's nowhere to go. We're just checking that the quantities obtained from exact diagonalization are the same as what you get from the field integration. Okay, that's the important thing here. Okay, so you'll notice in this illustration that for different confinement potentials, capital K, you have different colors, right? K over little k. You have the results that increasing the mass, we're increasing both masses uniformly, and calculating the Fi. And on this illustration, you have straight lines which correspond to exact diagonalization, and you have the markers which correspond to field theoretic results, right? So they sit right on top of each other. They approach the correct asymptotes, which are given by this expression where the first term is just the sum of the mode frequencies for a pristine system, and the second term is the energy if one of the masses is infinitely heavy. Okay, so as we crank up the masses, make them infinitely heavy, we approach these asymptotes. Okay, so all right, fine. So we seem to have an agreement between QFT and exact diagonalization. We can also put it on log scale to see what happens if we reduce the mass. Okay, they still agree. And of course, we can also check what happens when we change the confinement. If we, instead of having big K, we have big K plus some delta. And again, we see here that QFT and exact diagonalization agree. All right, so that's fine, right? Now, more importantly, let's see what happens when we crank up the temperature, right? We fix both masses, we set them to 10 times the original mass, and we start cranking up the temperature. And we see that the interaction energy goes to 0, as expected, right? Regardless of what the confining potential is. Now, here's the thing. Here's what I was mentioning earlier. Now we are changing the confining potential and increasing the temperature. And if we don't subtract the 0 Matsubara frequency, you get this linear drop, right? Which seems like as you crank up the temperature, the interaction gets stronger. This is the free energy that you're plotting, right? If you were to remove this term, okay, if you were to add back your TSI term, you see that both the field theoretic result and the exact diagonalization still agree, right? So that 0 Matsubara frequency term agrees exactly with that compensatory term from the exact diagonalization, okay? So you'll notice in, for example, in Pavlov's paper, one of the references, when they talk about the interaction between two potential wells, right? I mean, it's the confinement type interaction. They always say, oh, it decays with distance. Again, it's because they're dropping the 0th Matsubara term, okay? So again, the diatomic molecule is a contrived example. You'll never use it to actually calculate, position-dependent interaction. That's silly. But the takeaway here is that we can get an agreement even for such a limited system, right, between QFT and exact diagonalization. Now, more interestingly is if we do the same thing for a monoatomic chain, okay? So we can do it at 0 temperature and at finite temperature, okay? So what we have is we have two defects of mass capital M, which is given in terms of the original mass of the system, which is 1. And we see how the interaction energy changes based on separation, right? So you see here, we're putting it on a log-log plot. And you see that at 0 temperature, the behavior looks like a quasi-power law, right? So the upper dashed line goes as 1 over distance. The lower dashed line goes 1 over distance cubed, okay? And it's a known result that at large distances, regardless of what the masses of the impurities are, the interaction at 0 temperature will approach the inverse cube, right? And it smoothly goes to inverse cube, okay? Now, if you crank up the temperature a little bit, you see that over here, right, our interactions start kind of dipping faster. As we said, increasing the temperature leads to a faster decay. It suppresses the interaction. Now, again, these masses are obviously not stationary, right? They're just heavier or lighter, right? So this calculation is not done for infinitely heavy masses, right? That's the important bit. And we can see that, quasi-power law here, and then a kind of power law going to an exponential suppression at higher distances, okay? Similarly, we can do the same thing for a confinement potential, right? Again, here, this line is 1 over distance squared. At small distance, at 0 temperature, you get a quasi-power law. At finite temperature, you have even a more dramatic change, right? Stuff kind of drops down faster, okay? All right. Now, what we've done in this work, which wasn't done before, is we can actually look at the mixed configuration, where you have one mass defect and one confining potential, right? Look at combinations of how these two defects interact with each other. So again, at 0 temperature, you still get a quasi-power law. As you raise the temperature, you get faster decaying stuff. Okay, and again, the takeaway here is that interaction energy between impurities decays faster than between confined wells, and same story as always, higher temperature accelerates the decay, always. Okay. Now, we can also take a look at the sign of the interaction. So as Justin was alluding, right, that it's attractive, generally. That's not always the case, actually, right? So by playing with how you modify your perturbation, you can actually get attractive or repulsive interactions. So for example, on the left, what we have is an sign, or an interaction magnitude between two wells sitting right next to each other, right? So you have two confining potentials, the right one and the left one, and we can see that the sign of the interaction is always negative. Okay. Now, if you have one well and one impurity mass sitting next to each other, again, this is at 0 temperature, if the impurity mass is lighter than the mass of the pristine system, you get a repulsive interaction, the red stuff here. Otherwise, it's attractive, the blue stuff here. Okay, so you can change the sign of the interaction. And it holds also if you have two mass impurities with different masses. You can change attractive or repulsive based on how they compare to the mass of the chain. Okay, so that's doable also. We can also do a diatomic chain, which is quite fun. So here we have a chain composed of two types of masses, M1 being equal to 1, M2 being equal to 3, and we put a pair of impurities of 1.8. And as you see, if we were to fix the heavy impurity and we slide away the light one, or fix the light and slide away the one that's on the heavy, we get an oscillatory behavior, right? So you can have a positive, negative change of sign, depending on whether this guy replaces a mass that's heavier than itself or lighter than itself, right? So the idea is, if both of your masses, which are replacing the host atoms, are heavier or both are lighter, you get attraction. If one is heavier than the mass it replaces and the other one is lighter, you get repulsion. Okay, so what matters is the sign. Sorry, excuse me. In a sense, whether both are heavier or both are lighter. Both impurities are heavier or lighter than the masses that they replace.
So I guess you're saying here that if I have electrons which are lighter than the masses of the atoms around me, then this would correspond to attraction? No. I'm getting confused now. No, you've successfully confused me. Would you say this again?
Explain again.
I'm confused.
Yes, if you have a chain of atoms, all are say mass 1, right? Let's say, and I bring two impurities. One is mass 2 and the other one is mass 2. I plop them. They will attract. As long as both of your impurities are heavier than the atoms of the system, they'll attract. As long as both of those impurities are lighter than the masses of the chain, they will also attract. Now, if one of your impurities is lighter and the other one's heavier, they'll repel. Does that clarify it?
Yes. Why?
Why? Okay, because if you sit down and actually, when you work through the results, what you get, the terms you obtain in that logarithm, you get 1 minus. So essentially, your perturbation itself either is positive or negative, right? So to a leading order, the interaction is a product of these two things, right? Like if you think back to our lambda term, right? Our lambda term, if you're replacing your original atom by a heavier term, is going to be positive. If you're replacing it by a lighter term, it's going to be negative. To a leading order, the interaction between two impurities is a product of these two lambdas.
Yeah, no, you should move on.
Okay. Oh yeah. Okay.
Yeah.
Now it turns out that despite the oscillation here, right, as you know, it becomes non-trivial, the actual decay follows a power law, right? The envelope of this oscillatory function is still a power law. Okay. As before, at 0 temperature, it's a quasi-power law, and at a finite temperature, you still get a suppression, as before. Okay, so we can treat diatomic systems, we can treat systems with more sophisticated phononic dispersions using our formalism, right? Which is sort of the big benefit here, right? Which was not possible before. So again, while the interaction sign can oscillate, you know, there's still quasi-power law behavior. Now, if you look at earlier works, right, they also studied higher dimensions, but they did not do exact diagonalization because it's kind of tricky. So you'll realize here that in higher dimensions, you have also kind of a quasi-power law behavior, right? And at higher separations, you get an exponential suppression, right? So similar. And also for two potential wells, you get a similar result, okay? So you have a transition from, you know, let's say 1/r to 1/r times exponential. So also works. Now, these results were obtained diagrammatically in an approximation of a phonon dispersion with a constant velocity, right? So they just did a linear dispersion. Okay, so final bit, short thing. This is like from, you know, this week. So Justin was asking about dynamics. So one of the things that Phonon Casimir effect is famous for, right, is that you can actually bring the plates together, right? That's the crazy thing. Now here you can't really think about it in the same way because really your atoms are bonded. You can't really move the atom. You can't rip it off because there are some chemical potentials. There are different energies involved here, right? So what we can look at is what does the motion look like? Right, so what the best we can do is look at the covariance of the positions, right? Let's say the atoms can't actually leave their positions, but they'll probably vibrate differently, right? Once they see each other, right? So if you write down your expression, you can write down the covariance between two displacements as follows, right? It's just this term. You rearrange things, you get this. Now this bit, this expectation value in the middle, you'll realize that it's back to our psi's that we defined way in the beginning. Okay, so not going to bore you too much with this. This is, we can, in a sense, obtain the covariance between two positions. This is our key result here. Okay, I'm going to show you a couple of plots just to get a feel of what that means. Okay, so the covariance between the two displacements of two atoms is given by the pristine contribution and this correction. Okay, so first things first, if you have a covariance, this is done for a monoatomic chain. So singular purity, monoatomic chain. If we look at the covariance of a variable itself, is just a standard deviation, right? Obviously. So here, if the left plot, it tells you the temperature dependent standard deviation of the displacement of the atom that's been replaced by an impurity. Right, so we take an atom at some position, replace it by a heavier impurity, and we see its deviation of its displacement with temperature. Right, and obviously, as the temperature goes higher, it becomes linear. Which again makes sense. That's your equipartition theorem. You also see that if you step away about 14 sides to the side, the impurity is still there. You can also see what the standard deviation looks like there. Now clearly it's a little bit bigger because this mass is lighter, right? So you can see the signatures farther away. You can also look at correlations between two impurities. Now as a reminder, correlation is just a covariance divided by the product of standard deviations. Right, so if you have two impurities separated by 14 sites on a monoatomic chain, you can see that by cranking up the temperature, the correlation acquires this form. Now you have the black line, which is exact diagonalization, and the red dots, which is QFT results. right? Both are done. Both are computed here, show the agreement. And on the right-hand side, you can see that by increasing the masses of the impurities for a fixed temperature, the correlation also increases. Okay. Now, again, these results are a bit half-baked. They show the agreement between QFT and exact diagonalization, but as far as intuition and analysis, I'm still thinking about what that means. Okay. Now, with that, I would like to close. So the main development here is we propose a general formula to describe interaction energy between impurities in the system. We managed to validate our results using exact diagonalization. As far as one should care about this, I think it's really cool. It's really nice. And maybe, some clever experimentalists can figure out a way to actually measure this. And as far as where this is going in the future, maybe take a look at different kinds of perturbation and maybe explore non-equilibrium regime. And thank you very much. Apologize for going over time.
That's fantastic. No, I think you're right on time, actually. Yeah, so thank you very much, Sasha, for this very interesting talk. Any questions, especially from students, but it's also okay if faculty ask questions as well, but I won't hold it against you. But if any students want to ask questions, that would be great.
Alex, I had a question about when you fixed heavy and light masses. Can you go to the slide?
This guy?
So here you said that if your impurity mass is, both of your impurity masses are smaller compared to all the atoms in the chain, then they attract. And if both of them are heavier than relative to all the mass in the chain, then they attract, and otherwise they repel, right? So in the plot here, what you're doing is you have your three values, capital M. What does that represent here? Because I'm assuming that M1 and M2 are the impurity masses, two impurity masses that you're talking about, right?
No, M1 and M2 are the masses of the diatomic chain, right? So one of the masses in the diatomic chain is 1, and the other one is 3, and they alternate 1, 3, 1, 3, 1, 3. The impurity itself is the capital M, which is 1.8, and it's chosen in such a way that it's heavier than one of the native masses and lighter than the other, right? So if we were to choose our capital M bigger than 3, then you would not see this oscillation. If we chose it smaller than 1, you would also not see this oscillation.
Correct. Okay.
Right. So we chose it specifically that way to show that depending on whether this guy is heavier or lighter than the mass it's replacing, you're going to have this oscillatory behavior.
I see. Thank you.
So actually, what determines the period of this oscillation? Is it just one atomic mass? Sorry, so one atomic distance? Or
yeah, every site. Every site
just goes up and down, basically.
Yeah.
I see.
It's a seesaw. Yeah.
Aleksandr, I have 2 questions. First is how strong is this effect compared to electronic Casimir effect? And second, if you again compare with normal 2 metal plates in vacuum, if you say have 2 pieces of phanonic material, would you be able to see some effects, or you need to have 1 piece of phanonic material with 2 defects?
So as far as how strong it is, it's fairly weak, and it actually, you'll notice that all the energies are given in terms of the characteristic frequency, right? So if you have a stiffer system, you're going to have a bigger result, right? You're going to have a bigger, stronger interaction. That's kind of step 1. So how much you can crank it up? I mean, yeah, that depends. Like I can't give you a good number because it's fairly weak and it drops off fairly quickly. Now, as far as your second question, whether you have 2 pieces of phononic material, what you really need to have is you need to have a medium, a single system through which phonons can propagate from one defect to another. So you really have to have a single system, because if you have 2 separated materials, right, there is no way for phonons really to jump from one to another. Unless you're referring to the paper from, I think, 2 years ago, where they used a combination of phonons and the proper photonic Casimir effect, where the membranes vibrated. and changed the spacing, as a vibration, and the phonons leapt from one to another via the kind of the changing cavity size. But in reality, if you want to do this, you really need to have a single system.
More questions? Yeah, so I maybe one last question for me. Could you explain from a physical standpoint, without having to appeal to maths, why there is this change in sign of the interaction when you have this special regime whereby you're in between these two masses, this diatomic chain? What's the physics there? Apart from having to say, okay, fine, it's a particular term in this particular expansion and stuff, that's very detailed. But is there a simple way of understanding this? And as a result, is there a simple way of understanding the oscillation as well?
That's a good question. I honestly haven't come up with a nice intuitive way to see it, because then what comes down to is the shift in energies, right? And that's the big issue that I've been kind of also wrestling mentally, right? Like, as how do you, because really all it is the energies with the impurities minus the energies without the impurities, right?
Yes.
And yeah, so really, like, as far as physically, yeah, that's something I need to think more to come up with a more intuitive way. But yeah, I don't have a good picture now.
Okay.
Yeah, but that's definitely something that'd be nice to come up with.
Yeah, no.
Because it almost looks like, right? It almost looks like in a leading order, like it's like charges almost, right? It's a positive times positive. It looks very similar to that. But why is that the case? It's wonky, right? And it's,
Yeah, no, I if it were as simple as just kind of, above the mass or below the mass of the, so if big M were larger than both the masses, or big M is much smaller than both the masses, you get a difference in sign. And you might think, okay, maybe this is a kind of effective medium theory kind of thing, and you can try to, but this feels, but it feels like there should be something there. But I don't know what it is.
I agree. Yeah. I agree. I mean, yeah, like from the previous references that I was, also considering and using for, for inspiration and help, it's sort of, the argument was very similar, right? It's like it looks like a charge almost, but I mean, that's just a contrived way, and it's a helpful way, right, to think about it. But I don't think it gives you much physical intuition, unfortunately.
I see. Okay, last call for questions. More questions from people.
I think I shell-shocked people too much.
No, it was a very kind of detailed presentation. I think people learned something from this. Well, if there are no questions anymore, last call, then let's thank Sasha for this very interesting talk, for teaching us the Phonon Casimir effect. Yeah, so thanks a lot. Thanks.
Thank you so much, guys. Thank you very much. I hope it inspires you, and if you solve it, let me know, because